try again. There was a problem with the slides. Yeah, I think it's working. Thanks. All right. Okay, welcome back everyone. So we are continuing with the IUCAA Introductory Summer School and Refresher course in Astronomy and Astrophysics. And my name is Debarati Chatterjee. I'm an associate professor at IUCAA. And so today we will be continuing the discussions on compact stars that we started yesterday. I will start with clarifying a couple of points that I noticed yesterday after my talks. So first of all, I watched the video and I saw that I said something wrong. So it's when I was talking about magnetic flux conservation, I said magnetic flux is, so the correct answer is magnetic flux is magnetic field multiplied by the area. So what happens is when a normal star collapses to form a compact star, then the flux has to be conserved. So the product of magnetic field and area has to be conserved. So if the area reduces by shrinking, then the magnetic field blows up. Okay, so that was about how the origin of magnetic fields in neutron stars. About moment of inertia. So someone yesterday asked a question. I noticed I didn't answer how moment of inertia is actually measured. So in this slide I showed yesterday, this is actually summarized. So one can measure relativistic spin orbit coupling. And so this is done by measuring its additional contribution to the advance of periastron. So imagine that this omega dot is the periastron, and so omega SO is this relativistic spin orbit coupling contribution going to the advance of periastron. And this actually is related to the moment of inertia. So this is how it can be measured. The other way it can be measured is from pulsar glitches. So yesterday I talked about rotational glitches, and so there are also estimates, so theoretical estimates of moment of inertia that is contained in the neutron star crust, and that is responsible for causing glitches. So measurement of glitches is also a way in which moment of inertia can be estimated. And also I measured precession yesterday. So precession is the movement of the neutron star around its axis, but this is precisional movement is also related to the moment of inertia. So that is also another way of measuring the moment of inertia. Okay, and once moment of inertia is measured, then it is proportional to mass times radius squared. And once you have mass measurement, then you can measure the radius. So that was the other clarification. And the last thing I also noticed that somebody asked yesterday about whether hotspots in neutron stars are similar to sunspots. So I mentioned yes, but this is what I mentioned was in the case of magnetic hotspots. Yeah, it's true that magnetic hotspots, it is similar because although the configuration of the magnetic field is different, but the cause of the hotspot is the same. But I also forgot to mention another very important source of hotspots, origin of hotspots, and this is in case of accreting neutron stars. So if there are neutron stars which are accreting matter around from another companion star, so the column there is the accreting matter falls on the surface of the neutron star by a column, an accretion column, and where it touches the surface is also where hotspots are produced. So this is another very important origin of hotspots that I forgot to mention yesterday. Okay, so let's continue with our discussion on compact stars today. So today we will be talking more about the interior composition. Yesterday we talked about multi-wavelength, multi-messenger astronomy. So how we can determine global properties like mass, radius, moment of inertia, etc. from observations in electromagnetic multi-wavelength or gravitational waves. So today we will see how those measurements can actually help us to understand the interior composition of neutron stars as well as white dwarfs. So yesterday I showed you this rough diagram of the interior, but today we will delve much more into the details. So yesterday we already talked about the Fermi, so the degeneracy pressure. This was also very nicely explained in Professor Dipankar Bhattacharya's lectures. So we know that compact stars are stabilized against gravity with the help of the degeneracy pressure. And degeneracy pressure is, one second, I will just move this. Okay. So degeneracy pressure is something that stabilizes the star, and this is caused the yesterday I already explained to you that it is basically the property of the fermions by which they exhibit this kind of pressure coming from which is originating from Pauli exclusion principle followed by fermions. So Fermi-Dirac statistics tells us that the number of states at a given momentum k per unit volume is can be written in this way, and this comes from statistical mechanics. So here you can see a picture so this is called a Fermi sphere. So if you depict the energy levels in a momentum space, then this is what it looks like. And this is what the probability looks like when you are calculating this as a function of energy. So what does that mean? That according to Fermi-Dirac statistics, all the at zero temperature, all the energy levels which are available will be filled up by the participating fermions. That means that they, instead of other types of particles, like for example bosons, which can be at the ground state, instead fermions, since they don't want to be in the same energy state because of the Pauli exclusion principle, whenever you force these fermions into a certain energy level, they will always occupy higher and higher energy levels that are available up to the Fermi level. So in momentum space, it can be depicted as this filled up sphere, and this sphere has a radius up to the Fermi momentum. So this is what you can imagine the energy and the momentum like. So we look a little bit into the mathematics today. So the number of states at a given momentum k per unit volume can be written down using statistical theory, statistical mechanics in this way. Now, if you integrate out the number dn, then you get the number of particles per unit volume. So this is basically the number of particles per unit volume is what we call the number density. And this relation tells you that the Fermi momentum of the particle is actually related to the number density, okay, according to this equation. In a similar way, if you integrate over the energy levels, then you get an energy density, and this is also related to this Fermi momentum. Now, once you have the energy density, according to the first law of thermodynamics, there is a way of calculating the pressure. Okay, so it is related to the number density and the energy density. Now, if you have both energy density and pressure for a system which is at zero temperature, so compact stars, so neutron stars, which are cold, so they, when neutron stars are born, they are hot, called proto-neutron stars, and like I told you, so these emit neutrinos, become cold, and finally, when we observe a normal neutron star, it's cold. Why do we call it cold? Because the temperature of the neutron star is much less compared to the energies of the particles that are contained in its interior. So for a cold system, if you already have the energy density and the pressure, you already know its equation of state. So equation of state is nothing but it is a way of quantifying the interiors, or you can say it is a method of describing the interior of a neutron star, and everything that is a global property can be calculated from it. Okay, so once we have the equation of state, we can calculate from this everything else. Now let's look at a specific example. So yeah, the other thing you can calculate is the energy per particle. And this is nothing but related again to the energy density and the number density. So all these things are known once you know the equation of state. Now, a specific example. So this was actually explained in great detail by Professor Dipankar Bhattacharya in his lectures on stellar structure. So I will not go on to repeat it, but I will summarize the details here. So one specific example of this equation of state, which is very commonly used in compact star physics, as well as yeah, so for neutron stars and white dwarfs, and that is called a polytropic equation of state. What does it mean? It means that the pressure and density, we can describe it in a very simple form. And what simple form? So this is nothing but a constant times density raised to the power of gamma, so raised to the power of an index. And often this gamma is also written as 1 plus 1 by x, and n is called a polytropic index. So this is a parametrization of the pressure as a function of density. Now, it was demonstrated in Professor Bhattacharya's lectures that for non-relativistic electrons, so when velocity of the particles is low, in that case, this becomes a simple function rho to the power 5 by 3. So this gamma index becomes 5 by 3. Whereas in the special case where you have ultra-relativistic electrons or ultra-relativistic neutrons, in that case, this relation becomes rho to the power 4/3. Okay, so this is the case when you have very rapidly moving fermions. So like when the velocity approaches the speed of light. In that case, you have this simple relation. So these are the two extreme cases that you have for a polytropic equation of state. So if you plot an equation of state, this is what it would look like. So there is yeah, so there is a dependence of the pressure as a function of energy density. Now, like I said, why are we interested to calculate the energy density? This is because the energy density is from the energy density, one can compute its global properties. Like, for example, here in this example, once you have an equation of state, and the equation of state again depends on the interior composition. So all these different colored lines actually describe different interior composition possible in a neutron star. And then you have, if you have these equations of hydrostatic equilibrium, then you can map them from the equation of states directly onto the global quantity, like for example, mass and radius. So here this specific example shows you that if you have equations of state of this form, what would be the masses and radii, and how you can compare them with observations. Okay, so this is how it looks like. So the core composition gives you the equation of state. Equation of state gives you global properties, which in turn also depend on the exterior spacetime. Now, normally for white dwarfs, you have already heard this in the stellar structure lectures, that for the Newtonian case, like for example for white dwarfs, the stellar structure equations are one can easily calculate them. And the reason is because there are, for hydrostatic equilibrium, you need degeneracy pressure to balance the gravitational force, right? So here, for example, the pressure gradient dpdr, so this is the change in pressure with respect to change in radius, as you can see in this cartoon here. This and is related to dmdr, and this is the change in the mass with respect to change in radius. Okay, so these coupled equations actually give you the from this you can calculate the structure of the star. So you can try this simple example if you substitute P by a polytropic equation of state. a non-relativistic one, for example, and then you start to integrate it from the center towards the exterior, and then the value of pressure, so the value of the radius at which pressure becomes zero is called the radius of the compact star. So this is how the structure of the star can be calculated. Now we take a specific example. So we already talked about polytropes. So polytropes have this simple form, P equal to a certain constant times density raised to the power and index. Now, how about we try to solve this analytically and see what we get? So you see that for this Newtonian structure equations that we just saw, dPdr and dmdr, what if we try to eliminate one of them and make a single Poisson-like equation? So this is what it would look like. Okay, so if you substitute, say for example, you substitute m by using this equation and plug it into this equation, then you get a Poisson-like equation looking like this. Then a mathematical trick can be applied. In order to plot this analytically, what we need is we want to make it dimensionless. So let's define R as zeta times some characteristic radius, and we will calculate this characteristic radius later. So zeta now becomes our dimensionless radius. And we can similarly write down, say, rho of R as now a rho of zeta, and which is now written in terms of a function theta times rho c. Okay, so again, theta is dimensionless and rho c is a characteristic density. So now if we put these dimensionless quantities here, then we get an equation in terms of these dimensionless quantities, which is just a mathematical quantity, and that can be plotted. So this tells us that the characteristic radius that we get from this equation is nothing but a quantity that is given here. And we are left behind with once we define an RC like this, then we can eliminate a number of terms and we are left with a simple mathematical relation. This is commonly called the Lane-Emden equation. And subject to boundary conditions which are given here. So theta n vanishes at zeta equal to zeta n, and another boundary condition, theta prime is 0 at zeta equal to 0. So given these two boundary conditions, if you mathematically solve the Lane-Emden equation, this is what it looks like. So this is nothing but a solution, an analytical solution of the mass radius relation. So something similar to what you can apply in the case of white dwarfs, because we are talking about Newtonian structure calculation. Okay. Now, for the specific case of, okay, so let's also calculate, once you have the solution, you can calculate the mass by integrating from 0 to r over density. So this is what it would look like. And so if you actually solve this equation, what you get is an interesting relation and involving this index that you have in your polytropic equation of state. So this relation gives you some important limits. Okay, one limit is if you plug in the case gamma equal to 5/3. So this is what we already encountered. So this is the non-relativistic limit. If you plug in gamma equal to 5/3, you get m r cubed equal to constant. Okay, so this is an important relation for the non-relativistic limit. Now let's see what happens when you have 4/3. So if you can see already from the index of R that if gamma is less than 4/3, then the sphere becomes unstable and collapses into a black hole. Now there is a limiting case of stability, and this is the case when gamma equal to 4/3. So if you put gamma equal to 4/3 here, you see that the second term disappears and you have a m equal to constant relation. So this is actually what corresponds to the Chandrasekhar mass in the case of white dwarfs. So if you consider the specific case of electrons, so you will see that this is nothing but the Chandrasekhar mass. So I just want to remind you that the Chandrasekhar mass was the first limiting mass that was calculated for white dwarfs. Later, this work by Chandrasekhar was actually extended by several other studies, which showed that Coulomb corrections, thermal effects can also affect this value slightly. Okay. And so this is not an absolute number, but definitely the idea behind the Chandrasekhar mass remains the same. Also, general relativistic effects for white dwarfs. As you know, white dwarfs are also compact stars and they have strong gravity, although not as strong as neutron stars. But white dwarfs, if you consider general relativistic corrections, you will see that very close to this Chandrasekhar mass limit, there is a curving of this relation, but it does not affect this value too much. There is a small dependence on the GR effects. Finally, magnetic fields can actually have a very strong effect. I'm not going into too much of the details, but I myself have personally worked on this for quite some time. So there are discoveries of super Chandrasekhar white dwarfs, and so these have so these can have large masses. And it was thought that probably it is the magnetic field that supports these kind of super Chandrasekhar white dwarfs. And these discoveries of super Chandrasekhar white dwarfs was also very interesting because earlier it was thought that type 1A supernovae that involve white dwarfs and another companion star. So these are called standard candles in cosmology. But then if you have super Chandrasekhar white dwarfs, then this actually affects the standard candle hypothesis. So this got a lot of publicity some years ago, and I was also one of the people who looked into the effects of magnetic fields on white dwarfs, and of course, magnetars are also another very important application of strong magnetic fields in compact stars. And what we found was that magnetic fields actually have a very strong effect on the stability of and the mass of white dwarfs. Okay, so right, so let's continue with our discussion. So now let's look at what happens when we go into the territory of neutron stars. So now, as you know, neutron stars are have much stronger gravity, so they are much more relativistic. And so now we cannot neglect the GR effects as we were doing in the case of the white dwarf. So how do we include full GR effects into the hydrostatic equilibrium equations? So basically this is done by solving the conservation of energy momentum tensor equation. So if energy momentum tensor equation T mu nu is written in this way, where E is energy density, P is the pressure, U is the vector. So you must have encountered this equation, the fluid energy momentum tensor in the lectures of Professor Shukanta Bose. So the conservation of energy momentum tensor equation looks like this. And you can actually solve it to determine the hydrostatic equilibrium condition. And if you compare those hydrostatic equilibrium equations in full GR, you will see that they are actually not very different from the case of the Newtonian case, but there are a few correction terms that appear. So also Professor Dipankar Bhattacharya showed these Tolman-Oppenheimer-Volkoff equations, as they are called, of relativistic hydrostatic equilibrium. So you can see that there are these additional terms. So instead of m, there is m plus 4 pi p r cubed. Instead of e, there is another condition from p. And also in the denominator, instead of r square, there is another factor of minus 2 gm by c square. These are appearing, and you can check dimensionally if you do a dimensional analysis that these are actually having the same dimensions. Okay, so for example, p times r cubed. So this has the same dimension as energy, as mass or as energy. Okay, and p and e. So usually for these kind of calculations, we use something called natural units, where g and c are set to 1. And you will see that makes calculations much easier. So length, time, and these are having the same dimensions. Okay, so yeah, right. So this Tolman-Oppenheimer-Volkoff equations, these two coupled equations now are our relativistic hydrostatic equilibrium equations for in the case of full genuine relativity. In the same way as white dwarfs, now we can integrate these coupled equations starting from the stellar center, r equal to 0. At the stellar center, the mass is also 0, but the energy density and pressure are not 0. They have a certain central value. And then you integrate out towards the surface, and the value of the radius where pressure reduces to 0 is called radius of the neutron star, and the corresponding mass is called the stellar mass. Now, if you do this calculation for a simple, say, a polytrope, you can try this out and see. You will find very interesting results. So you can we can summarize what we find here in this bottom figure. So the mass and radius, if you plot them, you will see that for a free Fermi gas of neutrons, the mass only comes to 0.7 solar masses. Now, we will come to, I think yesterday we already had a look at the list of masses that were calculated for neutron stars, that were measured, sorry, for neutron stars. And you saw that they have a canonical value around 1.4. And the maximum, the highest maximum mass that was observed until now is close to 2 solar masses. So this definitely does not explain those high masses if you have only a free Fermi gas of neutrons. The other thing to observe is that in this branch of the mass and radius, not all points are stable. And the reason is that dP over dE, so P and E are related by the equation of state. And this relation is actually the speed of sound, the square of the speed of sound. And this speed of sound, you know, is limited by the value of speed of light. It cannot be acausal. It cannot exceed the speed of light. So from this, actually it tells you that there is a stable branch of this mass radius relation going up to the maximum mass, beyond which at this mass radius curve is actually unstable. Okay. So we have to find what ingredient we are missing in the calculation of the maximum mass, if we just consider a free Fermi gas of neutrons. So now we consider, let's look at what were the constituents of the neutron star in the first place. So the constituents were not only neutrons, but there were also a small fraction of protons and electrons. So now we ask ourselves that there is a very small fraction of protons and electrons, which is because of chemical equilibrium and charge neutrality. Okay, and so what is the origin of this? So the origin is the fact that neutrons in general in vacuum, and neutrons are unstable through a process called beta decay. So neutrons decay to protons, and they have a lifetime of 885 seconds, and producing electrons and electron type neutrinos. So these neutrinos can escape. Now, the reverse process, electron capture, is also possible. And this means that protons would capture electrons to produce back neutrons and electron neutrinos. Okay, so these two are inverse reactions. Now, what happens in infinite nuclear matter is that this is the kind of matter we consider in neutron stars, so infinite nuclear matter. So here you have you can have actually these energy levels. So neutrons actually, when they decay into protons, there have to be certain. So actually, equilibrium, chemical equilibrium is established when both of these processes can be taken into account. And this, according to statistical mechanics, this is possible when the chemical potentials of neutrons is equal to the sum of chemical potentials of proton and electrons. The other thing we know that any astrophysical system has to be charge neutral. Otherwise, Coulomb forces itself would disrupt the star, no matter what its what is the force binding the star. So charge neutrality also tells you, since neutrons are neutral, so the number of protons should be equal to the number of electrons. So this is the other condition also that we have to satisfy to have a stable neutron star. So even if these are accounted for, you will see that still the mass, in fact, the mass actually reduces further. So definitely this was not the ingredient that explains 1.4 or 2 solar mass neutron stars. So what are we missing? So we have considered a free Fermi gas of neutrons, we have added charge neutrality and chemical equilibrium, but still we are not able to explain the observed masses of neutron stars. So what is missing here is actually nucleon-nucleon interaction. So this is a very important ingredient that we must include in order to be able to explain the observed masses. And this is another reason why we consider neutron stars and as an astrophysical laboratory for studying nuclear matter under these extreme conditions. Okay. So there are many theoretical models for nucleon-nucleon interaction, but I will tell you why these are so difficult to calculate. Okay, so there are two major categories of nucleon-nucleon interaction. So by that I mean the interaction between the neutrons, protons, neutrons and neutrons by themselves and so on. So there are some class of models called microscopic models. Here, realistic nucleon-nucleon interactions are calculated. So there are processes, so there are these calculations like meson exchange, chiral perturbation theory. So these are all rigorous methods. And these interactions fit the properties of the models to scattering data which are observed in experiments. The other type of model are called phenomenological models. Phenomenological, in general, means that there are some, the models have some parameters, and these parameters are adjusted so as to reproduce nuclear observables that are actually seen in experiments. Okay. So now let me explain to you why only this information coming from nuclear experiments is not enough to be able to explain everything in neutron stars. So for that, I have to show you this diagram, which is actually a phase diagram. So just like you have for water, you can also draw a similar diagram. This diagram has density versus temperature. So whenever you have different phases, like for example, water, ice, and water vapor, you can draw a similar phase diagram that explains the conditions. Similarly, for nuclear matter also, one can draw a phase diagram. So if you look at the bottom axis, this is density, and this density is actually expressed in terms of the saturation density of matter, and this y-axis is temperature. So nuclei or nuclear experiments, they happen around 1 time saturation density. On the other hand, compact stars actually, they span this entire density range. So going all the way from nuclear experiments to several times normal nuclear matter density. Okay. But also the other thing to notice is that these are both at 0 temperatures. So they are both cold. On the other hand, you have other experiments. For example, accelerators. So I will talk about this very briefly. Accelerators, like you must have heard about the LHC experiment, the Large Hadron Collider, the RIC experiment. There are also upcoming experiments like FAIR at GSI in Germany, NICA, and so on. So all these heavy ion collision experiments actually probe matter, which is hot and dense. So they lie somewhere in the intermediate region. Okay, and then beyond this, there are many possible different phases of matter that can appear at very high densities or very high temperatures, like similar to the early universe conditions and so on. So this will tell you that all this kind of information we can get from these nuclear experiments or heavy ion collision experiments, they are not at the same conditions we are looking at for compact stars. So when so for neutron star matter, we need an equation of state that is at low temperature, so T equal to 0. It is at high density, which is 2 to 10 times saturation density. And the other thing is this third axis that you see here. This is the difference between neutron and proton number. This is also called anisotrope. I'm sorry. Um, this is called asymmetry. Okay. So now you see that these heavy ion collisions, etc., they are all having the same, or nuclear experiments, they have all the same number of neutrons and protons. So this is another thing which is special for neutron stars, because as you know, neutron stars have way more neutrons than they have protons. So now you can get some information coming from nuclear experiments or heavy ion collision experiments, but you need to extrapolate them to unknown territories of large densities and large asymmetries. So this is something which produces uncertainty in the models, and therefore they cannot be directly applied to compare them with observations. But observations can actually give you an idea about these uncertainties in the models. Okay. So nuclear experiments, they tell us a lot about binding energy, right? So we talked about iron having the highest binding energy for nuclei. So this kind of binding energy also gives us an idea about, so this is also something that can be measured in nuclear experiments. So in general, so now we are going into the realm of nuclear physics. So this is the fun part of neutron stars. We went from general relativity to particle physics, and now we are in nuclear physics territory. So in nuclear physics, we know that binding energy is actually the difference between the masses of nuclei and between free neutrons and protons. Okay, so this is something that binds the nucleus. So this was actually, there is a formula for it that was proposed by Bethe and Weizsäcker. And it tells you basically that for infinite nuclear matter, there is a term which is actually coming from the volume and another term coming from asymmetry. And this is related to delta, and delta is nothing but the asymmetry. So we can actually write down the energy per particle of neutron star matter as a Taylor series expansion. So all these are coefficients of these Taylor series expansion in terms of x. X is nothing but a dimensionless density, and another term in terms of delta square, where delta is nothing but asymmetry. So you see it depends on Nn minus Np by Nn plus Np. So for symmetric nuclear matter, so something that you have in heavy ion collisions or nuclear matter, or in nuclear experiments, so there you have the same number of neutron protons, so delta is 0. And if you have just pure neutron matter, so this is not ideally what a neutron star is, since we have a small fraction of protons and electrons. But imagine pure neutron matter. So in that case, you would have no protons, Np would be 0, and therefore delta would be 1. So delta is a quantity, an asymmetry, measure of asymmetry that goes between 0 and 1. So now you have this energy per particle of nuclear matter that can be expressed as a Taylor series of all these quantities. These are called empirical saturation parameters. And you have all these symmetry terms that are coefficients of the asymmetry. Okay, so very simply, so here you see at the bottom, these are things that are actually measured in, sorry, um, okay, yeah. So these are things that can actually be measured in nuclear experiments. So you see that there are these typical values that are measured for these coefficients. And energy per particle, if you plot it as a function of density, you see that N0 is actually the value, the saturation density is the value where you have the minimum of the energy per particle. And it corresponds to this value of minus 16 MeV for the case of nuclear matter. Now, symmetry energy is actually a very interesting quantity when it comes to neutron star matter. So you will see that there are a lot of discussions around symmetry energy, because neutron stars are actually one of the only laboratories in the universe where you can measure the effect of this quantity. So these terms can be estimated by studying matter which is away from equal number of neutrons and protons. So now let's look at terrestrial nuclear experiments. So nuclear empirical observables like the ones I talked about, NSAT, ESAT, all these parameters, nuclear empirical parameters, these are measured in terrestrial experiments. Which kind of experiments? So there are experiments which measure, study heavy nuclei, magic nuclei, and so on. So nuclei like, for example, lead 208, calcium 48, and so on. Some of these experiments are called PREX and CREX and so on. And they are giving a lot of interesting data about the symmetry energy and its derivatives. There are other experiments like, for example, these giant resonances of nuclei, monopole and dipole resonances. These also give us an idea about these empirical observables. There are also measures like electric dipole polarizability, nuclear masses, and so on. Okay, so there are many facilities at CERN and GSI, Ganil in France, INFN, GNIR, etc. So all these experiments give us an idea about the symmetry energy of nuclear matter. The other territory that I already talked about very briefly, so heavy ion collision experiments or accelerator experiments. So as you know that these facilities, like for example, you have at CERN, at GSI or Ganil. So here, accelerated beams of elements like or protons, they are smashed together to produce a spray of particles, and this actually generates a quark gluon plasma that thermalizes, and a lot of extreme kinds of physics can be extracted from this hot and dense environment. So so in order to understand this, now we are going into the territory of particle physics. So if we delve deep into the structure of matter, so this is given by the standard model. So atoms, as you know, are made up of electrons and nuclei. If you look inside nuclei, you have protons and neutrons, and these in turn are made up of sub nuclear structures called quarks. And the standard model also tells us that there are heavier cousins of neutrons and protons called hyperons. So these are also types of baryons. And these are normally in the world around us, we don't see these kind of particles. Okay. The reason is that they contain a heavy kind of strange quark. And this quark, so normally everything we see around us is composed of protons, neutrons, and these in turn are made up of up and down quarks. Whereas these heavy particles, heavy hyperons, are made up of strange quarks, and these are massive. So in general, in the densities we encounter on Earth, we don't see them, but you actually see them in heavy ion collisions. So strangeness is produced. This is something you see in heavy ion collision experiments, although momentarily. So these hyperons are seen to be produced momentarily, and then there are certain properties among these of these hyperons that tell you a lot about their which kind of hyperon you have observed. Okay, so now what we do is we try to put together all this information to construct the complex internal structure of neutron stars. So now it's like a jigsaw puzzle. If we put together all the information, this is what we think a neutron star interior looks like. So you have a cross section of the neutron star. So basically, the outer layers, as you are going from the surface towards the interior, the outer layers contain nuclei, so heavy nuclei like iron nuclei, and then and these are embedded in a sea of electrons. But as you are going towards the interior, then you have more and more deformed nuclei. So these are also funnily called pasta structures. So because they look like spaghetti and lasagna and so on. So these pasta structures are nothing but deformed, heavily deformed nuclei, finally melting into a homogeneous fluid in the core, the outer core. So made up of free neutrons, protons, and electrons. But if you go even further, so this is still around, say, 2 times saturation density. If you go even further into the interior, so beyond 3 times saturation density, now you can imagine having all these kind of strangeness containing structure that you saw momentarily in heavy ion collisions, but these are now stable components of the neutron star interior. And the reason is that for the densities that you have in the interior of a neutron star, strangeness can be conserved, and it can actually produce these kind of hyperons, quarks, and so on, all these kind of exotic components as stable components of the neutron star core. Now, the question is, can we actually observe, or the observations we saw yesterday, can they actually tell us something about the existence of these kind of strange objects, these kind of strange components? The answer is yes, but it's kind of like a convoluted answer. So you have to look for it. So we actually tried to look for signatures of the presence of these kind of particles in the observations. So one example of this is maximum mass. So if you put hyperons in the center of a neutron star, typically production of a new channel of equation of state reduces the pressure, and therefore correspondingly, if you calculate that from the top equations, TOV equations, you can calculate the masses, and you will see that there is a corresponding reduction in the masses. So now all these are in the figure of the masses as a function of radius. You see these are all these different masses which correspond to different models, and the ones which typically correspond to the ones containing hyperons, they would fall short. Now we need some observations to tell us whether or not hyperons can satisfy these kind of mass observations. And you can see on the left hand side all these observations, and it is true that there are recent observations as large as 2 solar mass that cannot be explained if there are free hyperons. So hyperons, even if present, they should have a very strong repulsion, vector repulsion amongst them, in order to be able to justify such large maximum masses of neutron stars. These kind of objects, these kind of strangeness containing matter can also affect cooling of a neutron star. So we were talking about these beta decay processes. So all these processes, for if only neutrons and protons were present, then we would have a standard cooling like you see here. So this is the luminosity as a function of temperature. So it would have this standard channel of cooling. But if you add in some special processes involving these hyperons or quarks and all these strangeness containing matter, they would actually enhance the cooling, and therefore you would have a different kind of rapid cooling. Okay, so observing temperatures of neutron stars as a function of time, this will also give you an information of what is the interior composition. What else? Okay, of course, gravitational waves. So this has opened up an entirely new window to the universe. And with gravitational waves, now we are being able to look directly into the interior of these objects. So yesterday, one of you asked what would be the observables if you have these kind of mode oscillations. So these images will explain. So on the left hand side, you see these mass versus radius plots for different kinds of equation of state. Among these, actually, this BBS2 and G240, so this red and green line, these contain hyperons. So you can see that they have lower masses. And now if you look at the F mode, so this is the fundamental mode, and this is something that can be observed, measured in gravitational wave observatories. And the observables in this case are the frequency and also the damping time, tau f. Okay, so nu f and tau f, these are the observables. So if you now plot these quantities as a function of square root of the density or as a function of the compactness, then you can try to differentiate between these kind of different equations of state. So these, as you can see, if there are hyperons, so they are actually deviating from the nuclear case when you observe them in observe the frequencies. Okay, so so these kind of gravitational wave emission is also another way to tell if you have, although it's not an easy way, but this is a way to distinguish between different composition in the interior. Similarly, R mode emission. So this is a rotational emission, rotational mode instability in neutron stars, and so this is something also that that changes when you have hyperons in them. So these, if you have the strangeness containing matter, then you would have a different kind of instability window, which means that different relation between the critical frequency and the temperature. So this is another way of differentiating between strangeness containing matter and nuclear matter. There are many other types of ways also to understand, or different effect signatures of strangeness containing matter. For example, if they are present in the core, then core collapse and black hole formation would also be affected. If hyperons are present in the neutron star core, stability of the remnant of the binary neutron star merger, this would also be affected. This is something that has been established in several simulations, recent simulations of neutron star mergers, and so on. So there are many other ways of distinguishing between the signatures, to look for signatures of strangeness containing matter in observations of neutron stars. And the last thing that I would cover today is something very interesting. So this is now we are going into the realm of condensed matter physics. So superfluidity, as I was telling you yesterday, superfluidity is something that has been seen in laboratories since several decades now, and there have been extensive experiments which give us a lot of information about superfluids. So, like I said, superfluids, when they are put into rotation, they form these kind of vortices. And these vortices can be pinned to the surfaces. Okay. So, this is something, this is seen in laboratories. Now, in neutron stars, it is thought that they can also have superfluidity in its interior. And if there is superfluidity, then you can have neutron superfluid vortices, like you see here in this cartoon, or you can also have proton superconducting flux tubes. So this is something interesting. So something relating something you see in the laboratory with something that is possible in the neutron star as well. And again, can we find any signatures of this kind of superfluidity, existence of superfluidity in the case of in observations? So the answer is yes. So yesterday we were talking about the glitch phenomena. So again, like I said, so glitch is something which is thought that when you have this kind of vortices pinned to the crust. So vortices are lying in the core but pinned to the crust, and due to rotation, these are deformed, and at a certain point they snap, and there is an angular momentum transfer between the crust and the core. And this is what is thought to produce glitches, rotational glitches in neutron stars. So sudden jumps in the rotation frequency. So another recent finding that confirmed that superfluidity can exist is the observation of cooling in the Cassiopeia A nebula. So there is a pulsar in the Cassiopeia A nebula, and it showed a very strange kind of cooling behavior. So you see here in this plot that this is the temperature as a function of time. So when they were observing Cassiopeia A pulsar, they found that this star was actually cooling slowly, and so following a standard cooling method, and then suddenly it started to cool very rapidly. And it is thought that this is because of a superfluid phenomena, that this causes this sudden change in the temperature and sudden change in the thermal evolution. So this is also another way of looking for a signature of superfluidity in neutron stars. So, as you can see, that neutron stars are astrophysical laboratories. So, white dwarfs are still, there are a lot of open questions, like I was telling you about super Chandrasekhar white dwarfs, magnetic field effects, and other things. But neutron stars are definitely a cosmic laboratory that has so many intriguing questions that are yet unanswered. And the reason is that they encompass so many different domains of physics, like we already talked about today. So, from general relativity to nuclear and accelerator experiments to theoretical physics, so condensed matter physics, nuclear and particle physics, and so on. And of course, now we have multi-messenger astronomical observations encompassing from electromagnetic multi-wavelength to gravitational to neutrinos and so on. And all this give us so much information that helps us to constrain these uncertainties that still lie in neutron star physics. Okay. So yeah, so there is a lot to look forward to. Like there are many nuclear and hypernuclear experiments currently going on all over the world, which are giving us information about the interactions between particles in neutron stars. Yesterday, I also talked about many observations, many observational facilities that are being launched, several third generation gravitational wave detectors that are being planned. So all this is going to complement the rapid advancement of theoretical procedures also in lattice theory, in nuclear physics, and so on. And all this together will enrich our understanding of dense matter physics that is in compact stars. Okay, so thank you very much, and I will leave these books for you to read further about this very interesting and intriguing topic. So yeah, please feel free to ask me questions, or to also you can send me the questions via the Google form. Okay. So I already see some hands up. I will try to address this.
Good morning, sir.
Yeah, go on.
Am I audible?
Yeah, you're audible.
See, I have heard of this quark stars.
Yes.
Actually, are they? I suppose they are also compact stars, and some quark gluon plasma or something like that exists there, right?
Yes, so quark stars are actually, so neutron stars in general are they are bound by so there is also gravity, but quark stars are just bound by the quark matter interaction. So you can see here, I did not talk about these in detail, but in this mass radius plot, you can see there are some stars marked by SQM on the left hand side. These curves, these are self bound stars. So this is something that originates from pure quark matter. So I did not talk about this. This is something. I mean, you can also have quark matter inside neutron stars. So today I talked about these kind of stars. So these are also called hybrid stars. But yeah, as you pointed out, there are also these self-bound quark stars, which have a different kind of mass radius property, and they also tell us a lot. If they exist, they tell us a lot about quark matter interactions. Okay, are there any other hands up? I see some questions on chat. I will try to address these. What's the critical point of net change of pressure per density or radius to balance hydrostatic equilibrium between the gas and inwards pulling gravitational force? So this is something that so this, for the case of for the Newtonian case, yeah, for the Newtonian case, you can see here um, critical point of change of pressure. Yeah, so here basically, I'm not sure what you mean by critical point of change of pressure. So this is basically the change of pressure with radius, and this is your change of the measure of change of mass as a function of radius is also the measure of the gravitational change. So basically these two balance each other, and that is what gives you the stability in the star. So you see that as a function of radius at each point, to have stability, this has to be balanced, right? And then the radius where the pressure disappears is where you have the radius of the star. So that is the that determines the structure of the compact star. Okay, there's a question. Can you explain in the R versus M graph why there are multiple masses for same value of R at the start of the graph? Yeah, okay. So let me check. Where's the mass radius curve? Yeah, so here actually, so I was mentioning here, so there are these stable and unstable branches. So so this is all defined by the change of pressure with the change of energy density, right? So this is the segment where you have stable configurations where dp de, or the speed of sound squared, is actually stable or is less than the value defined by the speed of light. So in this branch, so if you see a mass radius curve, indeed you can have 2 points of defined by the same radius, but as you can see the masses are different. Okay, so this is actually these are all these all belong to the same equation of state, but these are stars with different central density. So the stars which are actually stable, which are observed, are somewhere between 1 solar mass and 2 solar mass. Okay, and within that, the stable branch actually defines your the neutron star mass. There's a
Good
question.
morning.
Yeah.
Madam, can you please elaborate on how these super Chandrasekhar white dwarfs existed? What is the magnetic field role?
Yeah, actually, I don't have a slide for that because this is not a very introductory level problem. But super Chandrasekhar white dwarf masses. So white dwarf masses, actually the entire mass radius relationship drastically changes if you have magnetic fields which are close to the critical mass that yeah. So for large, for example, for neutron stars, when you have magnetars, you have magnetic fields as large as 10 to the 15, 10 to the 16 gauss. For white dwarfs, if you have magnetic fields which are above 10 to the 8, 10 to the 9 gauss, then you have a very strong electromagnetic contribution that enhances, that actually supports a large mass, and your mass radius relation completely changes. So you can look into some of the recent literature, because this is still on the research level. It's an area of active research. You may not find it in the textbooks I mentioned because this is an introductory lecture, but you will have to look at some recent literature or archive to read more about this.
Thank you, madam.
Yeah, sure. Okay. There are also other questions. Uh, Okay, there are some raised hands. I'm not able to see it. Yeah. Okay. Shubhadeep, do you have a question?
Yeah, ma'am. Am I audible?
Yeah, you're audible.
Ma'am, you have talked about due to nuclear interaction, there are lots of elementary particles produced in the interior of the neutron star, like quarks and quark gluon plasma. But these elementary particles are itself have a very short lifetime and unstable also. And on the if I just take an example of quark gluon plasma, it lasts for only 10 to the power minus 23 seconds, as we know from the experiments of sun. So on the other hand, we are telling that neutron star interior are very stable. So is not these two things are itself contradictory or like that?
Yeah, so like I said, so in heavy ion collision experiments, these have been observed. So we know that these exist, but for a very short lifetime, like you said. But in the neutron star interior, you have density. So heavy ion collision experiments, you can see also from this from the plot of the phase diagram of nuclear matter. Heavy ion collisions are here, so they are somewhere between. Normally, what you see is somewhere between say 2 to 3 times saturation density, or nowadays there are experiments which will probe say larger than 3. But compact star interior that we are talking about, this is actually going up to 10 times saturation density, and at those densities, and if you consider chemical equilibrium, you can have these hyperons, quarks, etc., as stable components of matter. So these will have these will not decay. Okay. The other reason is that you can also see here in this bottom figure that there are these chemical potentials, and the balance of these chemical potentials actually determine what is a stable component of the neutron star interior. So in order to decay into another component, so for example a lambda hyperon decaying into a proton, you will also need to have free energy levels of protons. But what happens here is that because of chemical equilibrium, you don't have free energy levels to decay to. So there is this chemical equilibrium actually takes care. So not only chemical equilibrium, but charge neutrality. Both of these things, they play. It's like they both together determine what are the components, and these can actually become stable components of the neutron star interior, unlike in heavy ion collisions. Which is why this is such an interesting place to look for these kind of exotic components.
Okay, ma'am. Thank you.
There are a few other questions in chat. I will try to take them quickly. What was observed in Cassiopeia? Did the luminosity grow? No, Cassiopeia actually. So there was something called. I'm sorry. How can I minimize this? Yeah. Okay, I'm not able to. All right. So let me find the figure. Yeah. So this was Cassiopeia. Um, Yeah, so in the case of Cassiopeia, the pulsar that was observed, so this, so there was a sudden critical point beyond which the cooling started to rapidly change. And this is said to be due to Cooper pair formation and breaking. So this is something, Cooper pair is when neutrons or protons, they pair amongst each other, forming a superfluid. So this type of behavior is seen in laboratories for superfluid experiments, whereas in the case of neutron stars, this was predicted as one of the so this is one of the proposed channels of cooling, enhanced cooling, that can actually lead to this kind of a sudden cooling behavior in neutron stars. Although currently there is a follow-up of this observation being carried out, and I don't know about the status, but this last a few years ago, this received a lot of publicity as the like witnessing the superfluid fluidity in neutron stars. Okay, so there is another last question. So okay. Yeah, I think this has been answered. So if there are no other let me check if there are any other questions. No, I don't see any other questions. All right. So,
Ma'am, hello,
yeah,
ma'am.
yeah.
Ma'am, I have a question on Google Form. Can you please go through it?
Oh, sorry. Yeah. Okay. So, is glitch and QPO the same? If not, what is the reason of QPO's presence in the power spectrum? No, glitch and QPO, quasi-periodic oscillations, are not the same. Glitch is caused, like I said, it is thought that earlier it was thought that it's because of crust cracking, and now it is suggested that superfluids are the cause of this kind of rotational glitches, whereas quasi-periodic oscillation is something completely different. These are seen in power spectra, and so it's a totally different I mean this so glitches are something that are seen in the rotational spectra, whereas quasi-periodic oscillations are seen in the case of bursts or superbursts. Okay, so I did not discuss this today, but yeah, you can try to look into the standard textbooks that I mentioned. So these should be mentioning bursts and superbursts and associated quasi-periodic oscillations. Yeah, I could not cover all the aspects of neutron star physics or white dwarf physics, because they are really there is a lot to discuss. But I hope, in order to understand better, those who are interested will go through the relevant lectures of stellar structure, general relativity, etc., that were already discussed in these lecture school, and also consult the textbooks that I mentioned or the other lecturers have mentioned. And so I hope you will be able to appreciate these subjects much more. All right. So I hope you will enjoy the rest of the summer school. And yeah, so good luck with your research prospects in future. All right. Bye.